By comparing the current sound features to patterns it has previously learned, the machine estimates the most likely words being spoken at any given time. Among the key techniques used in this stage is the hidden Markov model. This statistical method is designed to handle sequences of data that come from a process with hidden internal states. In simple terms, while we can observe the result of speech, such as the sound itself, the underlying linguistic process that generated it is not directly visible. The hidden Markov model assumes that speech is the result of transitions between these hidden states, and it uses probability to predict which sequence of states is most likely to have produced the observed features. This method relies on a few important assumptions. One is that each sound segment depends only on the segment that came immediately before it, not on earlier parts of the sequence. Another is that the sounds can be modeled using fixed distributions that describe how certain features are likely to occur. Though these assumptions simplify the real complexities of human speech, they make it possible to model and recognize spoken language with remarkable accuracy. Automated speech recognition is a multi-step process that begins with capturing sound and ends with transforming that sound into text. Through the combined use of audio processing, mathematical transformation, feature extraction, segmentation, and statistical modeling, this technology allows machines to interpret human speech with growing precision. As this field continues to advance, the systems become more effective at handling natural speech, accents, background noise, and conversational variation, bringing them ever closer to seamless human interaction. In the field of speech and audio processing, one of the most informative representations of sound is the spectrogram. A spectrogram provides a visual map of how the frequency content of a sound signal changes over time. It is typically plotted with time along one axis and frequency along the other, while the strength or intensity of the signal is represented by variations in brightness or color. This representation allows complex audio signals to be interpreted visually, highlighting patterns that might be difficult to discern in raw waveform data. Spectrograms offer a way to observe the rhythm, tone, and articulation of speech, as well as to detect other acoustic phenomena such as environmental sounds. Advanced learning systems have been developed to work directly with these visual representations of sound. In particular, certain types of layered learning models have proven effective in recognizing meaningful patterns within spectrograms. These models, originally designed for analyzing images, are trained to detect features that correspond to spoken elements such as phonemes, syllables, or complete words. They can also identify nonverbal audio features, including background noises and sound events, which are useful in applications that go beyond basic speech recognition. Beyond spectrograms, several additional features can be extracted from an audio signal to assist in various tasks. The zero crossing rate measures how often the signal changes direction, crossing from positive to negative or vice versa, and can help identify sharp or noisy segments in the sound. Short time energy reflects how the volume of the signal changes within short intervals, providing insights into emphasis and rhythm. Pitch tracking is used to follow the fundamental frequency of a voice, which plays a critical role in capturing intonation, emotion, and natural speech patterns. Formants, which are resonance frequencies that shape the distinct qualities of vowels, are also essential features in recognizing and analyzing speech. In applications involving speaker identification, these features help differentiate between individuals. Each person's voice carries unique acoustic traits, such as average pitch, rate of speech, and subtle spectral variations. By analyzing these characteristics, a system can determine whether two audio samples came from the same speaker or different ones. This capability is useful in authentication, personalization, and forensic investigation. Another important area of language understanding is syntactic parsing. This process involves breaking down a sentence into its grammatical components and understanding how the words relate to one another. Rather than simply matching keywords, syntactic parsing allows machines to interpret the structure of language. This helps systems determine, for example, who is performing an action, what the action is, and who or what is affected by it. Parsing enables deeper comprehension of written and spoken language, providing the foundation for meaningful interaction and accurate interpretation. The combination of these techniques allows modern audio systems to move far beyond simple voice-to-text conversion. By capturing the nuances of sound and structure, they are able to analyze speech in a way that approaches human understanding. These technologies are central not only to speech recognition but also to broader language processing tasks, making it possible for machines to interact more naturally and intelligently with human users. As these systems continue to develop, they open new pathways for accessibility, communication, and real-time language analysis. Advanced learning systems modeled after the human brain are increasingly capable of solving complex problems by identifying patterns in massive datasets. These systems are constructed using layered networks where each layer processes data in a different way. As data moves through these layers, the system learns to interpret inputs, whether they are visual, auditory, or based on decision-making tasks. Over time, the model becomes better at recognizing subtle features and responding appropriately. This kind of architecture allows for applications in image recognition, strategy games, language processing, and more. A prominent area of development within this field is reinforcement learning. This method involves a digital agent interacting with an environment in real time, learning from trial and error. The agent receives feedback based on its actions and gradually improves its performance.